Yeah, so I'm going to share some code. What I'm really excited about is showing off some lessons learned from running high-stakes arms races, and like cool shit you can do when you've got silent alarm capabilities and the freedom to do deception. So if you're watching this on YouTube in your office and you don't want to see a hacker who's showing you code and using terms like cool shit, then this is not the presentation for you. This is a lovely little visual put together by our friends at Hewlett-Packard Enterprise, showing the effort and risk and the payout potential for various cyber crimes. And I'm going to use ad fraud as our example of a high-stakes arms race, because as you can see there, it's by itself in payout potential versus effort and risk. It's the magic quadrant of cybercrime, which is pretty cool. And it's not obviously hard to beat. So I'm going to spend some time talking to you about why actually perpetrating ad fraud is so sophisticated now, why this problem hasn't already been crushed. So we'll walk through some of the evolution in the emergent arms race and then talk about some techniques to crack it. To a certain extent, what I'm really going to show you here is how to make the numbers in digital advertising lie to the tune of millions of dollars. Also useful if you're considering switching careers. Here's the important thing. If you infect real people's computers, then you can turn the mechanisms of digital advertising targeting against the good guys. Like, bear in mind that big advertising platforms now have extraordinary identity information, right? Extraordinary levels of behavioral targeting. They have monster data sets and are known to employ some of the best data scientists in the world, are actually pushing the forefront of data science in many cases. So how do you beat them with your botnet? Well, if you've infected grandma's computer and grandma is logged into a social network, if she's buying things, if she's viewing emails that have embedded graphics, you know, email newsletters are great ways of trying to drop targeting data on you. Then if there's also a bot in the background of her computer, then the bot looks like all of those things. Because the advertising world uses cookies and device IDs really as a kind of weak form of authentication. So they've associated your cookies, your device IDs with a number of actions that you've taken, including buying stuff. So if there's a background process that also has access to your cookie store, then that background process doesn't look like some anonymous bot, it looks like you. So you can make these bots in the backgrounds of countless infected computers watch ads all day long. And that means that you can inflate the size of any audience. The market price for this is about a penny to 2 pennies per visit. So if you have a botnet that is capable of playing this game, it needs to be a pretty sophisticated one, I'm going to get into that. The product you actually sell is unique visitors. A 50,000 node botnet, which I don't really think is that hard to put together, can pull in 150 grand a year. So the reason why I'm making an example out of these operations is because of economics like this. It's attracted tier 1 operators. Like I just don't know of anything else that pays this good. You pop 50,000 Windows machines and you can pull in 150 grand a month? Like, that is a crime that scales. It scales so well that it has attracted some of the absolutely best practitioners, so we can make some awesome examples out of studying them. It's important to understand how this ecosystem works. There are a large number of essentially traffic washing middlemen that call themselves CPC ad networks. This is the cover story so that websites that want more visitors can buy those visitors through CPC traffic brokers and long tail ad networks. The crime really is about making bots watch ads. It's just kind of trafficked through pay-per-click kinds of mechanisms. That's because websites, by the way, ordinarily buy traffic. Websites large and small all want more visitors because more visitors means more ads served, which means more money. Legitimate ways of getting more visitors is, buying like clickbaity ads on social networks. I'm sure you guys have seen that sort of thing. Or, the related articles kind of links at the ends of articles. You can also buy search traffic. And you'll just have to trust me. I don't want to give you a primer on the ad tech ecosystem, but there's a lot of middlemen that purport to be like those guys who will sell you traffic, as I said, for a penny or two per visit, and the traffic will look really good. As I was laying out, traffic buying or advertising buying is mostly targeted, so people are not just spraying ads across the internet. They want to reach, millennials who are in market for travel. And because of that targeting, what you can do is, of course, you can find infected machines where you've infected millennials. You can also kind of manufacture these sorts of identities through something that we call cookie sweetening. You can use real people's cookies, or if that's inconvenient, you can delete those cookies. And you can drive your bot around to hit like some travel sites and do a search for luxury shopping Borneo, knowing that you're going to get third-party tracking cookies through all of the little breadcrumb trails that you're laying down, and then you visit the website that ordered the traffic that is meant to look like in-market travel intenders who are millennial, and you make a whole bunch of money. By the way, this means that infinite reach feels possible on the internet, and nobody's advertising buy, no matter how outrageously targeted, goes unfilled, which is cool, but again, counterintuitive because, as I was saying, ad networks tend to employ smart people and they've got badass data. So let's talk about how this is possible. Just your basic intuition is that fraud detection should mostly be about anomaly detection, like across many different fields. The state of the art in fraud detection is really about doing some baseline, getting establishing what's normal, and then looking for differentials off of that. But because infections are now basically 3/4 based on real people's machines, who therefore have real browsing history, real identity, then it's remarkably easy to make your bots look extraordinarily lifelike. Not only that, but because tracking is often so good that it gets down to like actual purchase history, well, if you've infected people who themselves buy things, then you make your bots look like they buy things. And then finally, you might think that AI can be really helpful here. No one's really been able to pass the Turing test very convincingly. But you don't need to write really great AI to make your bot look extraordinarily lifelike, because you can just program the bot to copy its pet human. Right? So you want realistic mouse movement, realistic time on site, realistic diurnal usage patterns. Just have your bot copy its local human, and then you'll have variation across the bots, and each one of them will look extraordinarily lifelike. So now, highly successful, $150K, $1 million a year kinds of operations are being very, very good at hiding in the noise. So let's talk sophistication. There are actually a remarkably large number of ways of making money in ad fraud these days. The most important one is, as I was saying, just manufacturing audience. It's literally about making it look like there are more people looking at ads than there really are. So I'm going to focus on that one. And it's not like this is a new problem. So the evolution that I'm going to talk about, really what I want to do is just model this arms race for you before talking about techniques to winning it. You've got to think about everyone who is trying to identify this fraud is really forming a kind of selection pressure against which Tier 1 adversaries have been adapting. So let's walk through some of that evolution. The easiest way to try to make some money by viewing ads would be to just script it, right? This actually does work sometimes, even today. This is an especially appealing option if you've popped a bunch of IoT devices, but it is trivial to detect. You can go one step up, where you're parsing more HTML, but you're still not executing JavaScript, that's going to be pretty easy to find also. Starting to get more sophisticated now, let's use some embedded web browsing frameworks. This is actually not such a bad technique. Even today in 2018, you can make some money using just embedded Chromium, embedded IE, putting it into some other process. You're going to have a real JavaScript runtime environment. So if you start also doing some synthetic mouse movement and other things, you can look reasonably realistic. There are a few operations that are still capable of getting away with this. But laddering up, next, why don't we use off-the-shelf headless browsers? Phantom.js is the obvious choice here. You can actually make Phantom.js look pretty damn realistic. You're going to have to suppress a few things that Phantom inserts to try to advertise itself as such, but with a little bit of modification, you're starting to look pretty damn realistic. But let's go up. Why not actually take an entire browser instance and just script it from the outside, much like you do with Selenium, which is used all over the place to actually test web apps? You can start making this really good with just a little bit of investment. One of the troubles with it is that the actual binary is a full browser, and you've got to update it over time. So you've got to push big binary blobs to all of your infections. So this starts to become kind of a maintenance hassle. System emulators are also pretty cutting edge right now. This is particularly great for manufacturing mobile traffic. So you've popped a whole bunch of Windows machines, but you run like an Android emulator in the background. You make them do a little mobile ad fraud. And this can be genuinely difficult to detect if you're automating your movements really from outside of the environment. You can embark on a custom browser implementation. So why don't we write a browser from the ground up? This was a theoretical threat model for us at WhiteOps, but then we actually found one in the wild that built a very, very sophisticated operation on top of Node, where instead of trying to emulate every real function of a browser, which is much too difficult, instead what they did is they simply reversed all of the popular functions that are called by various advertising analytics systems and just monkey patched like mad. So over time, they made this Node architecture with new libraries that they're adding to it all the time look more and more and more realistically like real desktop browsers. They would just intercept functions, and they knew how to respond like IE, like Firefox on macOS, like a variety of different populations in order to hide the noise. And I'm going to delve into this a little bit because now we can start getting into some real concrete examples of sophistication. And then finally, a hybrid bot design, I would consider this to be the state of the art, so we're going to return to this in a minute, can be based out of a server farm where you have complete control over the execution environment, and you're just using a residential botnet as a kind of SOX proxy as a service. So imagine running essentially a server farm exactly the way that you want, but tunneling all the traffic through ordinary residential machines. Let's look at just how sophisticated custom browsers can get. This, the methbot operation, which is something that we took down about a year ago, is that node-based operation that I was just describing, and it was making enough money early enough that at its peak there were quite a few independent developers that were adding new libraries to make methbot look more and more sophisticated. They operated on weekly sprints. We know this because we got into a little heads-up competition with them, and as they were trying to reverse us and we were trying to reverse them, like they were rolling out new techniques every Tuesday. It was impressive. How do we know these things? Well, something fun happens when you get code execution on your enemy's platform. And that's necessarily the case for us because we were adding essentially like arbitrary JavaScript to various advertisements running across the web in order to differentiate between real humans and real bots. And so a payload that we knew was going to end up on methbot, we could like toString because why not, right? But then they noticed that. And so they tried to catch our toString and fake it, which I thought was rather fun. So now, of course, there's sort of an infinite rabbit hole here. Like we can try to catch their catch of our catch of their catch. And it was fun to see their countermeasures. And really, I wanted to show this code especially to illustrate what happens when you have a multi-million-dollar well-scaled cybercrime, which is that you can actually have a multi-million-dollar counterintelligence budget, and it's in your rational best interest to do so. So we saw countermeasures that were very, very specific to WhiteOps. They even helpfully labeled their code. Now, let's talk about sophisticated approaches to IP diversity. I already sketched one approach, which is infect a whole bunch of real residential machines, either install your binary blobs or use them as exit points. But this is just some crazy shit. These guys had their Node.js binaries running out of a couple of different data centers. And ordinarily, you do not need like a crack squad of white hat hackers to find a data center based like server farm that's watching ads all day long because people don't live in data centers, right? So that's just gonna stick out as a weird statistical anomaly. So here's what these guys did. They're actually running out of just a couple of different data centers in a few different countries. But they made their traffic look residential because they just started poisoning RARs. This is an Afrinic. This is a real Afrinic entry where they had an astonishing large, like a lot of IPv4 space. I want to say about 700,000 addresses. And they broke it up into small chunks, and then they made new Afrinic, Apnic, they used a variety of different RARs, made new entries to make it look like subblocks were sold off to different people. Here's, for instance, a Comcast entry, right? So this block looks like it's being registered to Comcast, except in this case, Comcast has an email address that goes to adword.yandex.ru@gmail, which I didn't know was a valid Comcast address. Here's Time Warner, Verizon, AT&T, Cox, Charter, SQL, CenturyLink. Like they didn't leave anybody out. Here's a fun one. It's supposedly registered to Verizon, but with a phone number in the Seychelles. So here's how you can hide data center traffic and make it look like it's coming from residential ISPs from across the United States. This is not trivial. This took about a year to do at the scale of 700,000 IP addresses. Because you make a little money and you just start reinvesting it. Now, as I was saying, the ultimate approach, and this is the state of the art right now, is using real browsers, but in an operating environment that you completely control, and then using infected residential machines as proxy exit points. I'm going to describe this as the state of the art for today. So, to summarize, the way to make a multi-million-dollar bot operation that's doing ad fraud this month and next month and the month after and then the month after that, which is why this scales so well, is to pop real people's computers, suborn their IDs, and by the way, The bad guys have heard of AI also. Machine learning techniques are available to them. And if you have the capability of infecting, say, 1 million people's computers, you have a hell of a training set. In fact, in some ways, it's better than the good guys' training set, right? No botnet operator today is going, damn it, GDPR compliance. We're out of business. So, the big lesson is that if you're playing this game on the side of good and light, it doesn't really matter what detection techniques you have today. It's actually all about how you run the arms race. And arms races are all resource depletion games. There are actually only 2 ways to win an arms race. You either start with more resources and you stay that way, or you somehow tilt the arms race in your favor such that your side of the race, your per turn cost of adaptation, is substantially lower than the other side's. That's it, because winning an arms race is all about being able to run the arms race longer than the other guy, period. That's it. So there are only 2 winning patterns. Now, what do you do if your enemy is at least as smart as you, right, which is just a wordy way of saying, let's assume they're smarter, and is better resourced? Because if you have a cybercrime that scales, every day that you succeed is another day of awesome cybercriminal profits. And every day that we, the people in this room, succeed is another day we get to keep our stressful jobs. Yay! Looking human is easier than you think, as I established. And the game that we're playing, now I'm going to get very narrowly specific about WhiteOps, is a game that we must play in the open. So all of our adversaries know who we are, and we stop now a monstrous amount of ad fraud. So our adversaries are extraordinarily well incentivized to beat us. And as I said, the game is out in the open. Like we try to hide our techniques, but again, we assume a multi-million-dollar counterintelligence budget, so we just have to assume that anyone who wants to do ad fraud can identify the WhiteOps payload, and we have to serve it, which means that we have to give it to the adversary. So of course they can reverse it. Of course they can selectively monkey patch it. Of course they can monitor what their own machines are doing with our payload, and what is sent back to our servers. And again, let's assume that you can pop 1 million machines, okay? You don't need to use them all in the perpetuation of whatever your scheme is. You could take 10% of them and just sniff the traffic on the wire, right? And this is where we get to one of my favorite principles in defensive innovation, okay? Nobody cares about your breakthrough in unpickable locks, okay? Until it gets installed in enough places that it actually gets in the way of a committed adversary one day, right? So the world's best lock picker is not going to show you whether your lock is truly unpickable. He's not going to bother until it's finally installed in a door that he wants to get by, right? So innovation in defensive security can feature literally years of false signals of success until you actually get widely deployed enough that the best of the best bothers to teach you that your shit is actually not that good after all. Okay? Innovation of any kind, and this includes defensive security innovation, doesn't matter until it gets deployed, right? So, because wide deployment usually takes so long, we, as innovators in defensive security, have a bigger hurdle than most other innovators, right? Like anyone who wants to develop something that's widely adopted faces the ordinary challenges of product market fit. And then we face this extra challenge, which is that there's a large population that also actively wants to make our stuff stop working, but only once we succeed, once we actually reach market success. So How can we possibly play a game like that to win? Well, we can constrain the enemy a little bit. Our enemy must accept our payload. I laid out all the ways that they can try to defeat us, but at least they have to play our game, because if they refuse, if they like drop packets, well, they're just going to stand out like a sore thumb. Like, they have to look human, and humans do accept our payload. They do execute it, and they do post back. So you can try to beat what we're doing, but you can't refuse to play. And there's a formalization of games like this from US defense. Some of you may be familiar with it, the OODA loop. The winning pattern here is to use the old expression, is to get inside your adversary's OODA loop, which means that in effect, they're still responding to round 1 of the game while you're playing round 2. So are there some ways that we can apply that lesson here? Well, yeah, there are. If you have a parameter space of possible detection techniques that's large enough that you can essentially afford to burn them. So in our game, we can create a silent alarm, because in particularly this case, if we're trying to prevent botnets from succeeding at ad fraud, we don't actually need to prevent bots from watching ads. We just have to prevent them from earning money from doing so. So what that means is that the actual mechanism that we need to break is about the money transfer. It's not about stopping the HTTP session. So we can let a bot watch an ad, and we can let them sit there and watch 20 ads without sending a positive signal back to the adversary that we've actually caught them. Now, generally speaking, we can't forever suppress success-fail information back to the adversary, right? But we don't need to suppress it forever. There's a particularly magical answer to exactly how you get inside the OODA loop, which is that you burn your detection technique on a periodicity that is just slightly shorter than the feedback to the adversary. So in our case, our adversaries know that we're the ones to beat. However, we don't tell them that we've detected them. We can leave that judgment remote. They have access to the payload. They don't have access to the judgment. And if we're able to serve a dynamic payload, what we have to do to sustainably tilt the arms race in our favor is send a fresh payload on an update interval that's slightly smaller than the feedback that they eventually get about whether they duped us or not. So in that case, they, in effect, have to play round 2 of the game before they can tell if they won round 1. Then they have to play round 3 of the game before they can tell if they won the last round. We can keep that up forever, and that's how we sustainably tilt this particular arms race in our favor. Now, one of the reasons why we can do this is because we are playing the imitation game over the internet, where, let me just observe that browsers are just application containers that execute a very special class of program that's written in JavaScript, right? There are some remarkably similar application containers for mobile apps in the Apple and Android ecosystems. And so in every case, we have some Turing-complete operating environment where we get to send some blob of instructions. So the number of possible ways that we can play the imitation game in that environment is actually remarkably high. So as long as we don't have some static way of detecting remote malware, if we can alter our payload with a sufficiently large parameter space that we can consider every individual detection technique to be burnable at a high level of frequency, then, as I said, we can keep that arms race tilted in our favor forever. So can you apply this to your own kinds of security games? I think the answer is yes, if you can satisfy these two constraints. One, you can trigger a silent alarm. In other words, you can suppress feedback, real-time oracular feedback to the adversary. And you can disconnect the action that the enemy is taking from the benefit. So as I was saying, in the ad fraud case, we don't have to prevent a bot from getting an ad. We just have to prevent the payment. So in that situation, if both of these things obtain, then you can completely change the risk-reward calculation for the adversary. I'll put it to you that after the invention of hardened steel, no innovation in locks, now I'm just riffing on my lock metaphor, actually matters until the invention of the silent alarm. Because all lock complication past hardened steel only added time to the adversary. And honestly, if you have like 5 seconds to pick a lock, you probably have 30 seconds to pick a lock. Like, this does not substantially change the value prop to the adversary. The silent alarm completely changes the game, because now our adversary can't tell if he was caught, which means he cannot control his own risk exposure. So if you have a silent alarm on the exterior and a safe in the back, what you're doing is you're encouraging your adversary to just do a smash and grab, because they're not going to try for the safe because they can't tell if something bad is going to happen to them. So to the maximum extent possible, you don't want to just add another barrier that's kind of like an additional complication to the lock. Those things don't really help in arms races. What helps is silent alarms. And silent alarms are only actually actionable in this radical upset of the value prop to the adversary if that means that your mechanism of interrupting the benefit is something that doesn't itself turn into a real-time signal. So that is the general purpose principle that I most wanted to impart to this crowd with just ad fraud as my illustration. Thanks for your attention, guys. That was like 58 slides. Any questions before drinks, or should we like do questions over drinks? I swear that that's not a trick question.
Right now, you're limited in where you can deploy your techniques to the provider layer. If, just imagine a world, you have the ability to deploy something on endpoint somehow. Would that also be a game changer?
Ooh, yeah, I'm delighted that you asked. So you know, if you're writing malware, of course you get a copy of every antivirus package, right? Like, so you don't release your malware until you know you win, right? To a certain extent, what we were asking ourselves when we set up this new defensive system is, how do we do the opposite of antivirus, right? So can we use the fact that we're moving to this crazy SaaS world to provide some kind of malware detection service that disconnects the decision from the compromised endpoint? So then we can deny the answer to our enemy. Now, we would certainly be able to level up the game if we had broader endpoint execution. But what we would always want to retain is the decision, if you will, being remote. So what having greater levels of endpoint execution give you is a broader parameter space of possible detection techniques and therefore burnable detection techniques. If you only have like a dozen ways of catching your adversary, you're gonna lose. The question is when, and how big is the adversary's budget, right? So having multiple degrees of freedom in what you can check for and at what layer, in effect blows out that possible parameter space so that you can get it to be large enough that none of them feel precious. It's okay to assume that they've been reversed even before you have active evidence of it, and you just burn it anyway.
And there's also activities that the adversary has to do to get their benefit.
Yeah.
Like you can't make money selling spam unless you send a bunch of email.
Yeah.
People are going after C2 channels and things like that to try and shut down these things and protect them.
Yeah.
Because there's like an infinite rabbit hole of like
Yeah.
C2 hiding you can do. And is there a similar set of things here? Like,
Well, right.
that seems relatively straightforward.
Well, one of the things that really attracted us to specifically the ad fraud problem is that it scales silently. So it's been under-examined by the entire security community because spam results in spam. Like even your most badass banking Trojan that goes undetected forever, but results in money going missing. Like people tend to notice the money has gone missing, whereas with ad fraud, it's a form of theft where nothing goes missing, right? Actually, the numbers go up, so people might get bonused. So from the same compromised machines, you can make money this month and the next month and the next. You don't have to start from scratch so often. And of course, not all crimes have that property, but many of the top tier crimes do, right? And to a certain extent, the picture that I'm trying to paint here is an evolutionary landscape where it's like, yeah, there are all kinds of ways of making money, but naturally the most badass adversaries are going to be doing the most profitable stuff. And in all of these crimes where you succeed by going undetected, there's this extra kind of like advantage taking that the adversaries have over arrogant defenders, because I walked you through like different levels of sophisticated bots. Well, let's say that you built the most badass way of finding bots that are like Perl scripts ever, right? Well, somebody who's running some Selenium-driven botnet against you and beating you, they don't send you a postcard saying, haha, you're not catching me. Instead, you just see traffic that you're signing off on and believe is perfectly legitimate, right? There are precious few signals to the defender that they're getting beaten. In fact, you could misinterpret adversarial evolution as your own success, right? As your techniques get beaten, your detection numbers go down, but you can interpret that as the bots are gone. And that, of course, can lead to just crazy self-reinforcing delusion. Anybody else? All right. Thanks, guys.